Secure the connection point. We need that barrier locked before the next wave hits. This is one of the most challenging places on Earth to build battalions, and here, China took on the task of creating new land.
Before a single grain of sand was placed, engineers had to understand what was hiding beneath 40 meters of open ocean. The seafloor here is unstable, soft, and constantly shifting. A nightmare for any construction project. This region is also one of the busiest shipping corridors in the world.
Every construction decision had to account for global trade routes and navigation safety. Then there was the weather. Dros. Powerful typhoons strike this area multiple times every year.
Engineers analyzed decades of wind and wave data to predict the sea's most violent behavior.
Beyond engineering, the location held massive strategic and economic importance.
Every meter of this future island had to be planned before construction could even begin. And this was only the planning phase. The real challenge was about to begin.
Before building land, engineers had to answer one critical question. Can the ocean floor even hold it?
This seabed isn't solid rock. It's layers of soft mud formed over thousands of years. To understand the ground below, engineers began deep core drilling operations. Long steel drills penetrated the seabed, pulling samples from dozens of meters below. What if the samples revealed nothing but weak mud? Each soil sample told a story about strength, pressure, and risk. Would you proceed or abandon the project here?
But the seabed wasn't just soft ice, it was uneven. How do you build level land on an uneven ocean floor?
Engineers used load-bearing analysis to calculate how much weight the seabed could survive.
One wrong calculation could cause the entire island to sink over time. Would you risk billions of dollars on numbers alone?
After months of testing, engineers finally understood the limits of the ocean floor.
Was the seabed strong enough or barely acceptable?
Now they knew the ground could hold the island, but creating land was a completely different challenge. How do you create land where only water exists?
Before land could be created, the ocean itself had to be controlled.
The first challenge was stopping the waves from destroying early construction work. Engineers began installing massive steel ring barriers directly into the sea. These barriers define the exact boundaries of the future island. Precision was critical. Even a small alignment error could cause failure. Temporary seawalls were added to reduce wave impact and prevent sand loss. Without containment, pumped sand would immediately wash back into the sea.
Every section was reinforced to withstand constant pressure from moving water. The ocean pushed back relentlessly, testing every barrier and every joint. With the sea finally contained, the next phase could begin, creating land itself. Creating land in the open sea begins with one thing: patfill, an unimaginable amount of sand. These specialized vessels were designed to extract sand from the ocean floor.
Sand was pulled from the seabed, thousands of tons at a time. Every operation had to be carefully controlled to avoid damaging the surrounding environment. Once collected, The sand was transported directly toward the future island site.
Pumping systems pushed sand through long pipelines across open water. Pressure and flow had to be perfectly balanced to prevent sand loss. Each load added a new layer to what would soon become solid ground.
The scale of this operation pushed dredging technology to its limits.
But raw sand alone wasn't enough. It still needed to become stable land.
Fresh sand may look solid, but without reinforcement, it can slowly sink back into the sea. The first priority was preventing uneven settlement across the island. Powerful compaction equipment was brought in to compress the sand layer by layer.
This process forced out trapped water and increased the sand's load-bearing strength. In weak zones, steel cylinders were driven deep into the seabed. These cylinders acted like anchors, locking the island to the ocean floor.
Precision was essential to keep the surface level across the entire site. GPS systems guided every adjustment down to the smallest measurement. Each round of compaction brought the island closer to permanent stability.
With the ground finally stabilized, the island was ready for protection against the sea itself.
Each round of compaction brought the island closer to permanent stability. Reclaimed sand alone couldn't survive the ocean. It needed a solid foundation. Engineers drove deep foundation piles into the seabed to anchor the land. Each pile was carefully measured to ensure it could bear the weight of future structures. Cement was mixed with sand to solidify the island's core. This mixture increased stability and prevented erosion from waves. Vibration compaction machines compressed the mixture further, removing air pockets and loose particles. Each layer was treated carefully before adding the next, building permanent stability.
The combination of deep piles, cement reinforcement, and compaction created a landmass strong enough to resist long-term erosion. Engineers continuously monitored for any shifts or settling in the foundation.
With the foundation secured, the island was ready to face the full force of the ocean itself.
The open sea was relentless. Waves from typhoons could destroy the island overnight.
Engineers began constructing massive concrete blocks to shield the edges. Each block weighed several tons and had to be positioned precisely.
The blocks were designed to break the force of incoming waves.
The wave-breaking design reduced erosion and protected the soft, reclaimed land behind it.
Corrosion from salt water presented another challenge.
Special anti-rust materials were used on exposed steel and reinforcement bars. Every joint, every block was tested against simulated storm conditions.
Continuous inspection ensured the seawalls would withstand years of typhoons and tidal forces.
With the perimeter secured, the island was ready to support heavy infrastructure safely. With the island stabilized, engineers began preparing platforms to support future infrastructure.
Massive concrete slabs were laid to form the foundation of roads, buildings, and facilities. Each slab was precisely aligned and leveled using GPS systems. Drainage systems were installed beneath the slabs to prevent water accumulation.
The island's concrete platform was reinforced to support extremely heavy loads.
Saltwater corrosion posed a threat to metal reinforcements. Utility tunnels for power, water, and communications were integrated into the platform. These tunnels allowed essential services to run safely beneath the island's surface. Every platform section was tested to handle maximum load before the next phase began. With the infrastructure platforms ready, the island was prepared for the assembly of permanent structures. With the island ready, massive precast structures had to be transported and installed. Floating cranes were stabilized to prevent swaying from waves and wind. These structures weighed hundreds of tons and required precise handling.
Every movement had to account for the unpredictable ocean currents. Strong winds could easily disrupt installation, so timing was critical. Sections were carefully aligned using GPS and laser guidance systems. Nighttime installation windows allowed calmer seas and reduced risks. Every lift required coordination between multiple teams across the island and floating platforms. Precast structures formed the skeleton of the island's permanent infrastructure. With the major assemblies in place, the island was ready to face nature at full force.
The South China Sea could unleash violent typhoons at any moment, halting construction entirely.
Weather monitoring systems tracked wind speeds, wave heights, and approaching storms in real time.
When a typhoon warning was issued, work had to be suspended immediately.
Emergency evacuation plans were in place to move personnel safely offshore.
All materials and equipment were anchored or tied down to prevent damage.
Typhoons could last hours or days, causing unavoidable construction delays.
Once the storm passed, rapid restart strategies were activated.
Teams coordinated across the island to maximize efficiency during safe windows. Continuous monitoring ensured that progress resumed safely and quickly. With extreme weather managed, the island was now ready for its final tests and permanent safety checks.
With construction complete, the island faced its final and most critical phase: safety and durability testing.
Engineers aimed to ensure the island could last at least 120 years against the elements.
Load tests simulated extreme weight on every platform and structure. Sections of the island were deliberately stressed to identify weak points.
Corrosion tests examined the effect of salt water and humidity over decades. Engineers adjusted structures where weaknesses were detected, ensuring maximum safety.
Sensors and monitoring devices were installed to track the island's stability continuously.
Every test was meticulously documented to meet international safety standards.
With the final tests completed, the artificial island was officially ready to withstand time and the sea. Even after completion, the island had to be prepared for natural disasters and accidents. Engineers conducted impact simulations to test earthquake resistance.
Ship collision scenarios were analyzed to protect critical structures. Emergency drills ensured that personnel could respond swiftly to any incident.
All procedures were repeated until flawless execution was achieved.
Impact-absorbing structures were reinforced to withstand collisions or sudden shocks. Continuous monitoring systems track every vibration, movement, and environmental change. Sensors are embedded throughout the island to provide real-time alerts for maintenance or emergencies. Every precaution was taken to ensure that the island could survive decades of storms, earthquakes, and human activity.
After years of planning, construction, and testing, the artificial island stands as a